sorry, my mistake. I just forgot to start the record. I'll start again. So yeah. So today we'll go through temporal difference methods, TD0, TD1, TD lambda maybe a little bit, and then we'll do the relation between TD and MC, MC meaning Monte Carlo, and then we'll go to off-policy methods and then QLEM. So in temporal difference methods, you are trying to estimate the value function of a given state. So you have some estimated value function of a state, old estimation. You're trying to update the estimation, as you have said that instead of looking at the whole trajectories, sample of trajectories, what I do is I just take one sample, one step sample, and then try to update the previous steps value function using the next steps value function. That is clear. So I have hold of this state, okay, stated type plus update is so I want it to reach to this thing. I want it to reach to ES. This is my actual target. Minus yeah. So what I have now. So this is my target. So now yeah. So So now what I have is okay, this thing I can, instead of, okay, so here I'm going to do this. This is the target which I want to reach. So instead of doing this, what I do is I just estimate GT minus E old ST, and then GT is equal to RT plus 1 plus gamma RT plus 2 plus 7, and then I get G2 is equal to RT plus 1 plus gamma into E S E plus 1. So this is basically, yeah, so this is your Bellman equation. Get your Bellman equation here. So E S T. One term is your Bellman equation. So ES T. This is your actual EST actual target. So I replace this here. Then what I get is we had old ST plus alpha RT plus 1 plus gamma EST plus 1. This is your true value function. That is VOST. But this is also not, I do not know the true value function of the next step. So what I do is I use the estimate which I have till now to denote, yeah, so I use the estimate, old estimate which I have. So this is my, we had here. I hope this is clear.
Yes.
So this is your TD0 algorithm. Okay, so now there is something known as TD1 algorithm, which basically you take all the steps till your states have terminated. So that is TD1 algorithm. Then you have somewhere in between this TD lambda algorithm. I think sir in the next weeks will touch those topics also. So where instead of taking one step, you can take like V mu ST is equal to, we have old ST plus alpha RT plus 1 plus gamma RT plus 2 yes, 2 step, and then you subtract and then plus gamma square, we had old ST plus 2 minus we had old ST. So now this is 2 steps. So you're looking forward 2 steps. Is this clear? Is this line clear?
Yes, yes.
So you can do on till end. So once you do it till the whole trajectory you terminate, what do you get? You get
Monte Carlo.
you get Monte Carlo. So I hope that relation is clear. So now
Yeah.
what I'll do today first is I'll just last time we did a problem on Monte Carlos for single visit and every visit. I hope you remember that. So what I do
Yes, yes.
so we'll do Monte Carlo single visit, Monte Carlo every visit, TD0. TD one, okay, TD1 algo sir is not it in the class. So yeah, TD1, if not we'll do it next week. No problem. So we'll do every visit Monte Carlo again. We'll do first visit Monte Carlo again. We'll do TD0 and we'll see the difference now. What is actually going on. So all of these things you don't have an underlying MDPs. You don't know the underlying MDPs. That is the problem. That is the main actual true problem with RL. So you don't know the underlying MDPs. So I have some underlying MDP which I don't know. So my first episode, I have three states. I think I threw three states, A, B, and terminal state. So my first episode is A, B, B, terminal state. So this is 3, 2, minus 4, 4, minus 3. This is episode 1. Then I have episode 2. B, A, B, B. Minus 2, B, minus 3. Okay, so okay, let's do first visit Monte Carlo. I think everyone knows. First visit Monte Carlo. First visit Monte Carlo. Could you give me BA and BB values? Okay, so let's do that. So it will be 3,
2. 2 plus 3 minus 3, 0.
no 1. No? This is second. This is the first. From here. 2. This 2 will cancel.
Yeah, that gives
Minus 1.
2.
No, that gives minus 1. No?
3 plus 2, 5 minus 4, 1 plus 4, 5 minus 3, 2.
What? I didn't get. Did I write something? No? No. Okay, I'll write it down. You tell me is it correct or not. Minus 1 plus 0. 5, 3. Okay, plus 1 by 4. Okay. I'm doing every visit. Okay, sorry. Yeah. You're right. Go on. Yeah, so you'll get 2 plus 0 by 2.
Yeah.
Yeah, sorry. I was doing every visit. Okay.
Hey, that's why I was confused. Okay. B minus 4 plus 4, 0 minus 3 plus minus 2 plus 3 minus 1 minus 3 minus 4. Shouldn't that be minus 4 instead of minus 2? Is minus 2 minus 3 okay. Never mind. It's minus 2. Yeah. My bad.
Every visit MC. So BA, BB. Okay, so
So 2 again. 2 plus 2 minus 4 minus 2 2 minus 3 minus 1. Right.
minus 3. Minus 2. Minus 3. This is minus 3. Minus 11. Yeah. You want to so it's fine, right? So yeah, so next what we'll do is we'll formulate an sorry, Markov reward process. So now, yeah, how to do TD0? So TD0 is you uh, evaluate your values V, you take your values V, and then you keep on iterating this based on this thing. So we'll not do this. What we'll do is how to easily calculate what 2 episodes give you in TD0. I think Sarah has done this in class. So what is the Markov process I get given I have these 2 episodes? Okay, so I have 2 states, state A and state B, and terminal state and terminal state. So yeah, so once I'm in state A, one time I go to state A, one time I go to state B, 2 times I go to state B, 3 times I go to state B. So totally I'm in a state A 4 times. 1, 2, 3, 4. Out of those 4 times, one time I go to state A and 3 times I go to state B. So the probability of going from state A to state A is 1/4.
Yeah.
Then naturally 3 to A to B would be 3/4. Right now, the reward. So this is the Markov reward process that I'm making. Given that I just know these 2 episodes. This is not the original Markov reward process. This is the Markov reward process. Given that I know that these 2 samples have happened. So now, if I have another episode, then my whole MDP will change. Yeah, so reward. So when I go from A to A, the reward I get is 3. I go to A to A only one time and I get the reward 3. So my average reward is 1/4, 3. So I am writing probability of going from that state to that state, reward. A to B. So A to B, once I get 2, once I get 4, once I get 3. So this is 6/3. Times I go B2. Totally 4 times I am in B. 1, 2, 3, 4. Totally 4 times I am in B. Out of which 2 times I go to B, so 1/2. And 2 times I go back to A, so 1/2. No self-repeat time, I go back. And the reward -3 -3/2. So this is -3. And -2 -4. This is also -3. Okay, any doubt in how I formulated the MDP?
No.
What would TD0 give?
Okay, this MDP is generated using Monte Carlo, right?
This MDP is generated using given these 2 episodes.
Okay.
So now TD also does something similar, right? So you have value, you have initial value function 0, then you take one step, you do some
Right.
But
But the actual underlying process that we use to generate it here is Monte Carlo is basically sampling problem, right?
yes,
So we have sampled episode 1 and we have got this trajectory.
Yes.
And we have sampled episode 2 and we have got this trajectory.
Yes.
And with that we are building the said MDP.
Yes.
But if we are using TD0 and building the MDP at each time step, it will change.
Yes.
Because I'm going from A to A only, then only the state A will exist, and the next time step I'll go to B.
Yes.
So it'll iteratively build, right?
Yes.
Good.
Yes, you'll iteratively build, but what I'm saying is I'm not doing all the iterative calculations. I'm saying given this, so given that I start from state A and I go to state A with reward, I iteratively build TD0. I update V. Okay. Then
Okay.
from A to B again update this. Going from B to A again update this. Going from A to B again update this. Going from B to B again update this. Now terminated. And once I terminate, I have reached a V. This all updation of V's I am done using TD algorithm.
Okay.
And yeah, so now I have stored those V's, and I have not now for the episode 2 I've not again restarted my um, I've not again restarted my 0 comma zeros.
Mm-hmm. We are using the same old
Same
bees.
that I got till T. That I
Yeah.
got till T. And then in the second episode again I am using those values and updating it. So now my
Mm.
question is, where will that TD converge to? Like, what is the value at the last year I would get? Like, what is given that this episode, this many number of items.
Ideally, it should be the same
Same to what?
as Monte Carlo.
Oh, no. It will not be same. That is TD1. It should be
Okay.
TD1. So it should be same as Monte Carlo. You're right. When I have infinitely many episodes,
Mm.
infinitely many episodes using ergodicity, I can say that yeah, time scaling on the number of episode scaling, I'll be same as Monte Carlo. That you're right. In
Right.
these cases, we are never approaching. We are never saying that. But like, given only these two episodes, it will not be same as Monte Carlo. So what you'll get is, you'll get a Bellman equation type equation. So it will just get by solving Bellman equation. So it will be 3 plus 1 by 4 into VA plus 3 by 4 into VB, and VB you will get as minus 3 plus 1 by 2 into VB. I think if you solve this, you get VA is equal to 2 and VB is equal to minus 2. These two. As you can see, these are completely different to first visit MCs, every visit MCs, and the TD zeros. Make your MDP, solve the Bellman equation.
Right.
That is what you got.
Mm-hmm.
You can try out actually, like yeah, 0 0, you can try it out, 0 0, and then how using this, okay, this equation, uh, you can keep on updating. Take gamma equal to 1 and you have your reward. So first time you get 3 here plus 1 into, this is 0, minus the old, this is also 0, right? So okay, now you need to properly, yeah, this alpha would be 1 by n and then all. But yeah, if you use this thing, then you will converge to 2n minus 2. I think this was also done in class by prof in my prof, but sir had different episodes and I'm using different episodes, but I hope the concept is clear.
Yes, it is clear.
So, what I know, sir has not taught TD1. I think sir will teach TD1 later. But just before, what I wanted to say is, TD1 would converge to every visit Monte Carlo. So TD1 is something where you look at the whole. So instead of just uh, two steps, you look at the whole trajectory at once and then update it. So just for these two episodes, it converts to TD1, which is looking at the whole trajectory.
Mm-hmm. Yeah.
So this is TD0 and TD1. So I'll keep this short this time. So next I'll go to off policy. Off policy. Yeah, you guys have really doubt in off policy because yeah, so there is like code up part I'll try to show in the next week or the next week, because now so you'll have a series of algorithms and then I'll do a series of algorithms codes at the same time. Will try to show it. Maybe Manav is also with the next team. Manav is also trying to show. Will be showing codes, I think, today also. I think Manav will handle the code part, but in the theory part, if you have interest, Manav. But next week I'll also try to show some codes on all the different methods that we have done, just to give you an idea. Because than the code, I believe, is doing one time by hand and then going to the code is much better than directly jumping into the code. Okay. So off policy, there is nothing doing by hand, it's all theory. I'll just go through theory once again. It will be more this thing when you have samples. So you have expectation of fx. I'm sticking to the notations which Sarah is using in class. So this is equal to expectation fx dx by dx. This was this thing. So yeah. Then sir, this can be sampled version of fxi dxi by dxi. Equivalent. Yeah. So basically you use that. So xi's are your trajectories here. F of xi is your cumulative return given in trajectory. Given a trajectory or cumulative. Given a trajectory, your total return. P of xi is the probability that the trajectory on which you are calculating this happens given the policy pi, which is what you want to calculate. Like this is you're not sampling through pi, you're calculating the expected return over the policy pi, and q of xi is over which you are sampling mu. Okay, so now given a trajectory s1 a1 s0 a0 s1 a1 r1 s2 s0 a0 s1 r1 a1 s2 r2 a2, so on. So now according to my pi policy, first I'll have probability of S0. I can start implementing this like this. With some probability pi, I'll choose A0 given S0 with my policy pi. With some the policy pi into probability that I go to state S1 given S0 and A0. Then once I'm at S1, I'll choose A1 given S1. Here you are using underlying, there is Markovity you are using. There is only Markovity that we are using. I hope that is clear. S2 given S1 and A1 and so on. And this is your P of x1. So this is the given trajectory. Given trajectory, this is what you want to calculate. Like this is the expected reward for the policy that you want to calculate, but you're not able to simulate it. So you are simulated using a different policy, which is mu. Under the policy mu, you will get a different property. S0, mu S0 given S0, S1 given S0, and so on. This is the probability that the given trajectory has occurred, and underlying the condition that you are using the policy mu. Now, when you're trying to calculate this term, the expected term for fx using p, you will see that this ratio cancels out all the terms which led to the underlying MTP. So you're just, if you know the policy pi, and you know the policy mu, it's enough to calculate this term. You don't need to know the underlying MTP. So this is off policy. Do you guys have any doubt in the off policy calculations or how
No.
So Rollouts, I'll just do a quick recap. I'll not do the whole thing. If you have any doubts, you can particularly ask me. So you have S. Okay, so in rollouts, what you do is you first pick a state, and then pick a state, take all possible actions, number of times, and so number of times, then you'll get multiple trajectories for each action you have taken. So if you have n actions in one state, you take one action, you get n trajectories. One action n times, you get n trajectories. You take another action n times, you get n trajectories. So you have n actions, take each of the n actions m times, you get trajectories. Now, based on the m trajectories, calculate the average expected return for taking action 1. Based on the other m trajectories, calculate the expected reward when you take action 2. Like that, calculate the expected rewards for all those actions. Then you greedily come up with a policy when you are in status. So that is rollout. I hope that is clear. Rollout is something which is more than an MC, because you are like effectively searching everything. You're not stuck to one trajectory. But whereas MC and TD are basically one sample, you're updating each and every time you're sampling something. Like given a sample path, you'll have an MC update. Doesn't matter which state you start from, doesn't matter which action you take, doesn't matter what happens. Given a sample path, you'll always have an MC value function for the state given an MC, and also value function given TD. But rollouts are something different, where you take all the possible, you're searching all the possible actions. So take action m times, take action B, m times take action C, m times take action D, m times, and do average, and then pick the action and state A greedy. I hope you understand the difference, and if you have any doubts in rollouts, you can ask. So next, okay, so you understand the difference between learning and planning, right? Here, where in planning, what you're doing is you're exhausting your search, like you're searching each and every possible trajectory that could possibly happen, and then take your decision. In learning, you're not exhaustively searching each and everything and then calculating. You're just sticking to the sample paths and saying, okay, what is the most probable thing that could happen? And given these many episodes, I'll try to come up with the best suited MDP for that, and then calculate my value function, take my action according to that MDP. So next you had
The one doubt I have with respect to planning, are we always given the model in planning?
that's right. In the planning, even if you're not given the model, you'll have multiple trajectories. If you know the model, then you're done. Then no need to do planning also.
Right.
Because if you know the model, you basically have the whole trajectories. But in rollouts, in planning, what you do is you exhaustively search everything. Like there are problems in plan. Okay, so you remember in the last week we did when we had the model. Even then we did value.
Right, yes.
Right, we had the model.
Yes.
We used the model to actually iterate value.
Yeah.
So that will not be there. So you could do that same thing, value iteration, without the model. That without the model will come as this thing. So in planning and learning, both you won't have the model.
Okay. So as to what Sir said in the lecture, he said that we'll be given some kind of specification of the model or the model in time.
For planning.
So, yeah, for planning. So what would be given? What would be given with respect to planning? When do you decide to use planning instead of learning?
Oh yeah, okay. So when do you use planning and learning? So planning is something when you have exhaustive computational power and you have nice amount of competition into your state space, and you know what your state space are, you know what your actions will be, right?
Yeah.
If your state space and action are very small, like small number of things, you can try to do planning. In discrete domain, very small state space, very small action space, planning actually helps you work out, because suppose you have just some 10 states. Each state you can take only 2 actions.
Right.
Do planning. Exhaustively search on each and every state. State
Okay.
2, M trajectories, state 2, M trajectories, state 3, M trajectories, calculate expectation, 3D. That is computationally possible. Now suppose you have a state space which is like millions or some thousands, and each state space each state you have some 10 to 20 actions. Exhaustive search is very difficult.
Yeah.
Rollout, you need like really high-end systems to do rollouts on those.
Yeah.
Now all this what I'm saying is, you know the MTP but you don't know transition properties. So what is given to you is, you know the states, you know the state space, you know the
Yeah.
state space, you know all those things of an MTP, but what you don't know is what are transition probabilities. If you know the transition probabilities, then you can sit down and calculate the expected rewards for each of everything. No, making sense?
Yeah. Yes.
The main thing that you don't know is transition probabilities. What you'll be given is your state space, your action space. Based on that, you'll decide whether to do planning or not.
Right. Okay. Cool.
So upper confidence. And then you had upper confidence trees, right? Yeah. So upper confidence trees. So okay. So upper confidence trees we had. So similar way to UCVs, upper confidence bonds in multi-arm matrix, right? So now the confidence term amount to 2 ln by n in M multi-arm bandit. Here it becomes Cp into root ln T by L in Rm. Okay, now what is L in this case? Okay, what is T?
Number of samples.
Okay, specific samples.
Number of samples of a state that we take.
T, right?
Yeah. Yeah.
Okay, T, that is actually known as depth.
Okay.
Is the depth. It's number of samples, that you're right, but not number of samples in state. So you pick a state, and then how long have you by doing the rollout, how long have you passed the trajectory? It's basically the time inside the trajectory that you're currently going.
Right. Okay.
Or how long you have looked at each trajectory. There could be some RL where it's infinite. They don't have a temporal state. It's infinitely long problem. So you don't need to look at the infinitely long problem. You can just look at a part of the problem. So how long have you searched? That is that. And N is number of times you have taken the action.
Right.
So this confidence bound actually comes up over QSC. Now here in planning, instead of working on P, we are working on QSS. So your action would be, the next action, P plus 1, would be to choose R max A prime, QS A prime, plus Cp into root log n T by L. Yeah. Yeah, I think, yeah. Okay, so this is set upon, this n will be vary for each action. So now if you have one trajectory, if you have only chosen each action one time, and you are calculating the estimated amount, so this would give you expected reward given you have started at state S and taken action A1.
Yeah. Right.
Cp into the depth you have taken for that trajectory, given that you have taken S and number of times you have pulled the action. You have taken the action A prime. This is the number of times you have taken the action A prime. now you'll get one for A prime. Now next, you will, you're in state S, you take the second action that you can take. So this will give you the total expected reward given that you have taken S and the B, and then this N would be for the second action. This N would be number of times you have taken the Bth action.
Okay. Okay.
Depth would remain the same. Depth, it could also change. Depth could also change. Maybe it would happen as that maybe now you suppose you are in terminal state problem. When you've taken action A, it terminated at different time, and when you take an action B, it terminated different time. So it also comes into it.
Right. So we compute Q values for all the actions available at
Yes.
state S.
Yes, yes. And then just not the Q value. While doing comparison, you just don't compare the Q values. You're basically what you used to do is you compared max of Q values in the previous this thing. When you were doing last week when we were doing greedy, what you were actually doing was you were arc maxing A over all the QSs. QSs you were doing BS, but it's the same thing in the last because everything was written this time. BS QSA would have been the same. So, yeah, but actually greedily while going from value to policy, you do this arc max of A prime just the Q, just the Q, not the confidence term.
Yeah. Yes.
Now the confidence term comes up for each action from a given state. That
Right.
confidence term varies for each action.
Right. Yes.
And now you are clear on how upper confidence is right. And I hope you see that this is a planning problem, not a learning.
So how does that confidence term actually affect the LHS value or the action value that we're computing?
So more number of times you have sampled that action, more number of times you've taken that action, the confidence term would decrease, right? So that says that you are actually closer to the US of it.
Okay.
If you're not closer, then the confidence. So suppose this is not the true value actually. This is just one estimated sample.
Yeah. Yes.
So as n increases, this term would decrease.
Yes, definitely.
So that means that you have sampled a so many times that with high probability you have come to the true value. You want the confidence interval to keep on decreasing.
Right. So what it essentially does is that it guarantees with a certain probability that you'll reach optimal point.
Yes. If you will reach, it will guarantee with the probability that what you are calculating. So the Q function you are calculating, you'll reach epsilon close to. I think the pack formulation continues from the pack that you did in NAB.
Yeah.
Where instead of the pack formulation, instead of finding the maximum R, you wanted to find an R which was epsilon close with 1 minus delta probability.
Right. Yes.
The same thing is done here. You don't want to calculate the optimal policy.
Okay.
You want to calculate a policy which is epsilon close with 1 minus delta. Like policy matlab, you want to given that you're in a state S, you want to find that action which is epsilon close to the optimal action with probability 1 minus delta.
Okay.
I hope you see the resemblance between NLP and this.
Right. Yes.
There it was, I think, just the expected reward. Here it's not expected reward. It's the Q function, not the B function. Because
action values.
Yes. So next there was SARS. So I'll quickly go through. Okay, if you guys have any doubt on SARS and expected SARS and class, I'll just quickly go to parameters. So initialize this parameter for sample. All this case you initialize. Okay, then pick S0 and time T0 with some probability, that is P of S0. It doesn't depend on the entry, just pick the S0, it doesn't matter. Next, pick s e comma dot with epsilon b. Okay, so yeah. Then take UST comma 8 because now you've picked an action. Calculate UST comma 8 with UST comma 8 plus alpha into r t plus 1 plus gamma UST plus 1 comma plus 1. Okay, I missed an action. Pick action 80. After picking action 80, apply 80 to get S. Then again pick 80 plus 1 epsilon 3. Yeah, this step is crucial. Next, you minus 2 plus 2 comma 8. Do this again. This is new. This is old. Action. Okay, so this is SARSA. Do you understand the difference between rollouts, UCT and SARSA? You're actually doing the same, but instead of doing all for tag setting, you're just looking at those trajectories which have really good return values. So next you can change this hold with expected Q values. That is gamma summation ai pi st plus 1 comma a st plus 1 comma a. If you replace this, then this becomes expected SARSA. These are just multiple arguments. So now, which is better, which is not better, it depends. If computation of this part takes long, like you have any number of actions, or your action space is continuous, then you need to calculate integrals.
Right, yes.
So it depends which is better, which is not better. It depends. But it's a various types of algorithms. All of these algorithms converge to Q. Then you have Q learning. Q learning, I think in the next tutorial also I'll go more deep into it because now I'm running out of time, but I'll go more deep into Q learning also. So Q star st comma is equal to expectation of this one plus gamma. Okay, so the update function. That is the target variable. So the update function is Q st comma is equal to Q st comma plus alpha. My target is I want to reach to the update of this gamma maps over Q st plus 1 overall type minus Q st. You are just changing what is your target and you are writing. Yeah, so okay, let me just give a small okay, I'll give you a small table so that you guys could understand what actually is going on in each and every of them. Okay, so first I have what are my values that I'm estimating. Values estimated. Then I have okay, so then there are two policies. I'll limit planning and learning, but they are not planning and learning entirely. But okay, you'll understand why I'm limiting planning and learning. Okay, so now I have I estimate B pi. Right. So what I have is in planning, I have a state yes with some policy pi. We take all the actions. These are my actions. These filled just dots are actions, and then I go to multiple states with different probabilities. Then I calculate this thing. This is something similar to policy evaluation. It's not policy evaluation is not planning. So yeah, maybe this not this. I like expected returns or something like that. Expected updates. Yeah, updates. I update the expected. Remember last time when we were doing policy iteration, value iteration, we were finding the expected return given a policy or expected return given a value function.
Yeah.
So this may be known as sampled updates. Let's have a look at this. Okay. So for this thing you have sample updates is you have S, you have A, then you have SP. Just one. You're updating. This is TD0. In TD0 you are updating B1.
Yes.
Okay, so next is V star S. I think this is okay. So yeah, this is policy. Let's give it policy evaluation. Okay, so V star is when I'm acting greedily. So I have S. I have all my actions. I do all the these things. Now what I take is I take the maximum over those. This is also one kind of update where I update greedily. This is also we did greedily part also. This is value iteration. Or this is policy iteration. This is policy evaluation. This is policy iteration. Where you take the action based on maximum of those things. Here you are just evaluating the policy. Here you are evaluating the optimal policy. So you evaluate, you take the max greedily. You do this number of times, you assure that you go to this one. I hope that is clear. Okay, so next you have q pi s comma. Okay, so now when you have q pi s comma, the graph changes to s comma a. Okay, and then you arrive at different states. S primes with different probabilities and different rewards. Then again, you arrive at different. Okay. This I think this has not yet been taught. This Q for expected has not been taught, but Q for this the sample path has been taught. S comma A. You have a reward, you get S prime, and then you choose A. This is SARSA. You start with SA, you update SAs. How do you update SAs? You pick S1s, you pick A1s. You update SAs. Oh, okay. I think I might have confused you, but is that clear? These gaps I will fill later on when the algorithms sir mentioned comes in, but right now yeah. So what my main goal is to say is that in TD0 you no need to pick second action which you had to do while doing SARSA. In SARSA you had a term where you pick an action, then you apply action, you go to a state, then you also pick the next action also before
Yes.
that comes up because of this thing.
Mm-hmm.
Here TD0 you did not pick the next action. You just update V of S. Pick an action, do it, you go to S prime, update S. That is TLC. Whereas in SARSA, we can, action already is given. So do that action, you'll go to state S prime, then again pick A prime, and then update Q of S comma. I hope that is clear. Next Q star S comma A. This is, okay, maybe you guys can tell what this is. S prime. I do on, and then I choose max out. So I'm at S comma A. I get a reward R, I go to S prime. And then I choose A prime to complete. So what is this? maybe I have confused you guys, but this is Q learning. I just wanted to see the difference between what SARSA and Q learning is. But I think I have confused you guys.
No, I get that SARSA and Q learning are somewhat similar, but in the case of SARSA, we follow policy pi, whereas for Q learning, instead of summation over all policies,
All
we take a
policies.
maximum
Yes.
over actions.
Yes.
So instead of following Bellman equation, we follow Bellman's optimality equation.
Yes. Yes, you are exactly right. Actually, well put. This follows Bellman's equation. And this follows optimality. Optimal Bellman equation. Yeah, absolutely. That is. So, if you guys have any doubt, you can ask. I think I'm. From next week or next week, I'll try to show. I'll try to do algorithms, coding algorithm of this. But I just wanted you to first understand what actually is going on in each of the algorithms. You have any doubts in TD0, SARSA, Q learning, rollouts, UCTs? And you also see that SARSA and Q learning could converge to very different cases also. That also you could see, right? Like even you use Bellman equation multiple times, it will not guarantee that you'll get to the optimal point. But
Yes. So basically, I follow policy pi, and if I follow that policy infinitely often, I'll
yes.
converge to the same point. But
Yes.
instead, I'm taking max over actions here,
Yes.
which is why I'll converge much faster.
Yes. And all the convergence in this actually builds up from the two examples that we did last time for value iteration policy.
Right, yes. Makes sense.
Yeah, so now last time when we did one part of like when you're greedy, it's Q learning. When you're not greedy, when you just fix the policy and do it, it's SARSA. Similarly,
Right.
when you're greedy at each and every step and update the policy and go back.
Right.
So I hope that clears up.
But even in Q learning, I follow policy pi, but I still update Q star, right?
Yeah, you should update Q star. Yes. Yeah, so the subtle difference is it's not exactly the same, both the things coming back here, but that subtle difference is here also. In SARSA, you fix a policy and you work on that policy, which we did for value iteration.
On policy method.
Yeah,
Right.
yeah. So the on policy and off policy, all the sample paths are on policies, and all the expected updates where you do multiple trajectories and then come back. That is also on policy. Okay, now on policy. On policy is you want to.
When I use the policy pi and update the same policy.
The same policy, yes. But when you can't sample through policy pi while doing sampled updates, you can do it on policy mu, some other policy.
Right.
And then also calculate the expected rewards by using the off policy updates.
Right.
I'm out of time, but maybe you could give some feedbacks, like what do you want? Like, do you want more problems like this, or do you want me to go to code, or do you want some more theory part in this, or next time?
These problems actually help us understand what goes on underlying.
Yeah. So I wanted to do a short problem on Q learning and SARSA also, just to do the updates work in TD0. But the problem is you need to have that Q learning and SARSA, you have an epsilon greedy part, right?
Yeah.
So now you do same Q learning, I do same Q learning, we both will get different. It's not a
Yes.
stochastic algorithm. So I can't do hand by hand, because the moment I'm following epsilon greedy, I don't know with what sample path I generate. So
Right.
but I can try to do that. Okay. So yeah, next week I don't know what the topics are, but
Maybe not by hand, but maybe we can visualize that using a program of sort.
programs I think Mana will go through,
Yeah.
or if yeah, Mana will go through. But next time, yeah, I'll also make some programs.
No, just for the visualization part. The
Okay.
theories are actually help us understand these things. If both of you do programs, it will be kind of unbalanced.
Mm-hmm. Okay, so visualization, you want code just for one sample part, like how each step upgrades, like what was the
Yeah,
case before.
yeah, right.
Now,
Instead of drawing everything by hand and doing everything by hand,
yeah, yeah,
it'll be easier for you to generalize this stuff, right?
yeah, yeah. I agree. Okay, then yeah, next time I'll try that.
Cool.
Thanks for the. Okay, yeah, you guys can join Manav's. Okay. I'll be waiting for.